ever wondered if we could travel at the speed of light? Now, before we hop on this cosmic roller coaster, let's first understand what we're dealing with. The speed of light, a staggering 700 million miles per hour, is not just some random number. It's the ultimate speed limit of the universe. Nothing, according to our current understanding of physics, can exceed it. Now imagine you're in a car, the fastest car you can think of. You push the pedal to the metal, the landscape becomes a blur, and the speedometer needle keeps climbing. But no matter how powerful your engine, no matter how smooth the road, you'll never come close to the speed of light. It's like trying to reach the end of a rainbow. The faster you go, the further it seems to recede into the distance. And it's not just about speed. Light plays a crucial role in how we understand the universe. It's our cosmic messenger, bringing us information from distant stars and galaxies. It sets a cosmic clock, helping us measure time and distance in the vast expanses of space. And it's a key player in Einstein's theory of relativity, which revolutionized our understanding of space, time, and gravity. The speed of light, then, is more than just a number. It's a fundamental constant of nature, a cornerstone of our physical reality. Its invariance, the fact that it remains the same no matter how fast you're moving or where you are in the universe, is what makes it so special and so challenging to overcome. So why is this cosmic speed limit so important? Because it sets the rules for the cosmic game we're all part of. It tells us what's possible and what's not. It shapes our understanding of the universe and our place within it. It's a cosmic boundary that we're still striving to understand and maybe, just maybe, one day to overcome. But what happens if we try to push this limit? Strap in as we're about to take a detour through Einstein's universe. Imagine trying to drive faster and faster, but your car gets heavier with each added speed. Sounds bizarre? Welcome to the world of special relativity. This is where the mind-bending physics of time dilation come into play. You might have heard of the famous twin paradox, a thought experiment in special relativity. It goes something like this. There are two twins. One stays on Earth while the other boards a spaceship and travels near the speed of light. When the space-traveling twin returns, they find that they've aged less than their Earth-bound sibling. Why does this happen? Well, according to special relativity, time slows down for an object that's moving at a high speed. As the speed of an object approaches the speed of light, time for that object slows down relative to a stationary observer. This is known as time dilation. But that's not all. As the speed of an object increases, its mass also increases. This is due to the energy required to accelerate it. As you get closer to the speed of light, the energy required to continue accelerating increases exponentially. At the speed of light, it would require near infinite energy to maintain that speed. Now, you might be thinking, wait a minute, light travels at the speed of light, so does it have infinite mass? The answer is no. This is because light is massless to begin with. It's one of the quirks of the universe that something as insubstantial as light sets the universal speed limit. So, given the near infinite energy requirement and the bizarre effects of time dilation, reaching the speed of light for any object with mass seems like a Herculean task, if not downright impossible. But you might wonder, what about particles in particle accelerators? They reach speeds close to the speed of light, right? Indeed, they do. But remember, these are subatomic particles we're talking about, not massive objects like spaceships. So, with our current understanding of physics, reaching the speed of light seems like a distant dream. But what if we could warp the very fabric of space-time? Star Trek fans, you might recognize this one. Warp drives, a sci-fi dream or a future reality. Imagine a rubber sheet stretched taut. This sheet represents the fabric of space-time. Now place a marble on the sheet. The marble creates a dip representing the distortion of space-time by mass. In the universe, this is how gravity works. But what if we could manipulate this sheet, creating our own dips and peaks at will? Enter the concept of warp drives. Warp drives, a concept birthed in the science fiction world, have become a fascinating topic of exploration in actual physics. The idea is to manipulate space-time itself, compressing it in front of a spacecraft and expanding it behind. This would create a bubble of flat space-time where the spacecraft sits, allowing it to ride the wave of distorted space. The most popular model for a potential warp drive is the Alcubierre drive, named after Mexican physicist Miguel Alcubierre. His theory, proposed in 1994, takes advantage of Einstein's field equations in general relativity. It suggests that faster-than-light travel might be possible by warping space-time around a spacecraft. However, the Alcubierre drive remains a theoretical concept for a reason. It requires exotic matter with negative energy density, a substance that has not been discovered or confirmed to exist. Additionally, the energy required for such an operation is immense, equivalent to the mass energy of a planet like Jupiter. The engineering challenges are just as daunting, as we currently lack the technology to manipulate space-time on such a scale. Yet the concept of warp drives has pushed our understanding of the universe and its laws. It has sparked countless discussions, research papers, and theories, all aimed at pushing the boundaries of what we believe is possible. While warp drives remain in the realm of theory for now, what we have achieved is no less fascinating. Let's talk about particle accelerators. Subatomic particles like electrons and protons have already experienced near light speed travel thanks to particle accelerators. Now, you might be thinking, what on earth is a particle accelerator? Well, it's a kind of cosmic racetrack where particles are propelled to incredibly high speeds, almost reaching the speed of light. This isn't some far-off space technology. It's happening right here on Earth in laboratories across the globe. Particle accelerators are one of the few places where we've managed to touch the speed of light, albeit in a very controlled and limited environment. But why do we do this? Why push these tiny particles to such extreme speeds? The answer lies in the realm of scientific research. The world of the tiny and incredibly fast can tell us a lot about the universe. By accelerating particles to near light speeds, scientists can observe their behaviors, interactions, and properties under extreme conditions. This helps us better understand the fundamental building blocks of our universe. For instance, the Large Hadron Collider, the world's largest and most powerful particle accelerator, was instrumental in discovering the Higgs boson, a particle that gives other particles mass. This was a monumental breakthrough in our understanding of the universe, and it wouldn't have been possible without touching the edges of light speed. Now, don't get too excited. Just because we can accelerate particles to near light speed doesn't mean we'll be hopping aboard a warp speed spaceship anytime soon. Remember, these are subatomic particles we're talking about. The energy required to accelerate a spacecraft, let alone a human, to near light speed is currently beyond our reach. But that doesn't mean we can't dream. Theoretical physics gives us a glimpse into the possibilities of faster-than-light travel, and particle accelerators are a testament to our ability to push the boundaries of what's possible. So, while our dreams of Starfleet-style space travel may be far off, we're already exploring the edges of light speed in our own ways. So, can we really travel at the speed of light, you may ask? Well, as things stand now, the answer is a resounding no. Our current understanding of physics and technology simply doesn't allow for it. The cosmic speed limit, as dictated by special relativity, is an insurmountable wall for anything with mass. As we've discussed earlier, as an object with mass approaches the speed of light, its energy requirements skyrocket towards infinity. Concurrently, time dilation kicks in, causing time to slow down for the fast-moving object compared to a stationary observer. These phenomena present formidable challenges that we're yet to overcome. Then there are the theoretical solutions like warp drives, which promise to bend the rules without breaking them. They propose the tantalizing possibility of faster-than-light travel by manipulating space-time itself. But let's not forget, these are currently just theories and far from becoming practical realities. The hurdles are not just scientific, but also engineering ones. Building a warp drive, if it's even possible, would require materials and energy scales that are beyond our current capabilities. But it's not all doom and gloom. Particles and accelerators already travel at speeds incredibly close to light speed, providing us with valuable insights and practical benefits in the realm of research. These feats, though limited in scope, show us that touching the cosmic speed limit, at least in some capacity, is within our reach. And while the dream of traveling at the speed of light may seem distant, it's important to remember that science is always evolving. Ongoing research across the globe is relentlessly probing the mysteries of the universe and pushing the boundaries of our knowledge. Today's impossibilities could become tomorrow's breakthroughs. So, in the grand scheme of things, we're still at the beginning of our cosmic journey. Our understanding of the universe is still in its infancy, and there's a vast expanse of uncharted territory out there waiting to be explored. For now, light-speed travel remains a dream. But who knows what the future holds? After all, we're only just beginning to explore the final frontier.